Hello, students. Welcome back. So, in this session, we are going to be focusing our attention on imbalanced data. So, what exactly is imbalanced data? Well, it means that one class it has more samples than the other class. So, for example, let's say you have a data from a doctor. So you have the different patients, patient one, two, three, and all the way up to 1,000 patients. And this is a test one, test two conducted on each patient. And this is the cancer, whether the patient has a cancer or not. So in this particular instance, you have 900 patients that do not have cancer, but only 100 of them have cancer. So, in other words, 900 samples, they belong to class A, and for 100 samples, they belong to class B. So, this is an example of your imbalanced data set. It is not 50-50; it is 90-10 ratio. So let's take a look at some more examples of real life in real life. So suppose in a bank transaction, when people make transaction, let's say there are 10,000 transaction. So out of 10,000, maybe actually most of the time you will have normal transactions. So let's say 9,900. These are your normal transaction, and only 100 of them are fraud. So in this case, only 1% is fraud. So you have 9,900. These are normal, and only 1% that is fraud. Let's take a look at another example. 1,000 patient, the one I just showed you, 900 people are normal, only 100 people have serious disease. So in this case, only 10% people have the disease. These are some more examples. So fraud detection, medical diagnosis, even spam detection. So majority of email that you get is going to be good email. They'll be not spam. Then you have few emails that are spam. These are called minority classes. So why is imbalanced data dangerous? Well, suppose you have 10,000 transactions. 9,900 are normal and only 100 is fraud. In this case, only 1% is fraud. So if your model, it predicts every single sample as normal. Let's say you have a model that's going to predict this thing, that every sample is a normal. Then your accuracy is going to be 9,900 divided by 10,000. In other words, 99% accuracy. Well, that's not right. That's because your model, the one I just created, is predicting everything normal. So it is always going to give you 99% accuracy. So this looks good, but your model is useless because it's never able to detect the fraud. We are focusing our attention on the fraud one. So in this particular instance, your accuracy is misleading. Now, since your accuracy is misleading in imbalanced data set, so which metric should you use? Well, there are two of them: precision and recall. Precision, this actually tells you that out of the predicted positive, how many are correct. So the formula for precision is true positive divided by true positive plus false positive. On the other hand, recall, this tells you that out of the actual positive, how many were detected. And this is the formula for your recall. True positive divided by true positive plus false negative. These ones, they focus on these ones right here, the ones that are your minority sample. Now let's look at some of the techniques to handle imbalanced data. The first one is data level methods. In this case, what we do is we modify our data set. So one of the technique we use is called random undersampling. In this particular instance, what I'm doing, that we are removing samples from your majority class. So let's say you have 900 sample right here and you have 100 samples. What I'm doing, I'm only taking 100 sample from here. So 100 from this minority and only 100 sample from the majority, and this is how you get your data set now. So you have 100 and 100 of each one of them. So the idea is this, that you're choosing only a small subset of samples from your majority of class. Well, the advantage is this: it is fast, it is simple. Disadvantage: you are losing useful data. That's because you're only selecting the 100 sample over here and you're removing or discarding the other 800 samples that actually can contain, or they may contain, useful information. Now Python actually has a library called Imblearn. This allows you to perform undersampling. So I'm reading a CSV file. This is my X right here. I'm actually taking these features: test one, test two, test three. This is my feature space. And Y, this is my target. So there's a disease column. That's my target. So create a random undersampler. This is my instance. And in this instance, I'm calling this inbuilt method called fit resample. Supply your X and Y to that. And this is going to produce your X result and your Y result. This is your random sampler. So this basically is this right here. So it has produced a balanced data set. And then there's another technique called random oversampling. That's opposite of previous one. So in this case, what you're doing, you're duplicating the minority sample. So this is my 900 samples. This is my class A. This is my class B. And what I'm doing, I'm taking 9 times of this sample. So you take 9 times of this sample. So you're going to get 900 sample from here. And then you're going to get 900 sample from here, because I'm taking 100 times 9, that will be a 900. So this way now my samples is balanced. Problem is this, that this may cause overfitting. That's because this sample is getting multiplied 9 times. You can actually implement this in Python. So I'm reading this some CSV file. This is my X and Y right here. So these are my columns, X, test 1, test 2, test 3. In this case, just call random oversampler and call this method if it resample, supply your X and Y, and this is going to create your X res and Y res. So this one right here is balanced. So you're going to get same number of your X and Y. So basically, you're going to have same number of your class A and class B. And then you have another technique called SMORT. This is the most important one. SMORT stands for Synthetic Minority Oversampling Technique. Oh my God, that's a mouthful. What it does, it creates artificial minority samples and it does not duplicate data. So, in other words, it creates new realistic sample. So, let's say you have 900 samples right here, you have 100 samples of B. So, what it's going to do is going to create some random samples from your these minority sample. This way, your data set would be balanced. This is the idea. So let's take a look at the visual intuition of this algorithm. Suppose these are your points. Okay, so let's say these cross right here, each one of these crosses, right? This one, this one, this one, they represent class A. These are majority, and then you have these dots right here. This one, this one, this one, and these dots, these are your minority class. So the idea is this, that first you draw imaginary lines between nearby minority points. So in this particular instance, let's say my nearby minority point is this one and this one and this one. So I'm going to take this point, this point, and this point and draw a line. So that's what I'm doing over here. I'm actually drawing a line. There you go. So after the line is drawn, that's my step number one. Now, one thing I want to explain, that how do you find nearby points? In this case, I'm using K and N to find nearby points. Okay, step number two. Now you're gonna place randomly, you're going to put some new dots on these lines. So the lines that I just drew, I'm just going to put some dots over here. So let's say I put one dot over here, one dot over here, one dot over here. So these dots now, they are your new samples. So this is the idea of your SMORT. Now, Learn library has an inbuilt method called SMORT. So we can import that. So I'm reading the CSV file. This is my X, this is my Y right here. Create a SMORT instance, and then you just supply your X and Y. That's all it is. It's going to supply X and Y, and it's going to generate those samples for you. So this way, your data set now becomes balanced. Then there are algorithm level methods. In other words, what they do, they modify the model. That's what they do. So for example, class weighting. In this particular instance, you're giving high importance to minority class. So for example, if let's say you have class A with 900 samples and class B with 100 samples, then when you are feeding this data to the model is going to give this particular sample less weight. On the other hand, is going to give this sample more weight. So this is called class weighting. Now, these methods are implemented internally in your scikit-learn. So when you call your logistic regression model over here, all you have to do is just say class weight equal to balance. That's all you have to do. And then you can train the model. This is going to take care for you. In the case of decision tree classifier, same thing. When you call your decision tree classifier, specify your class weight equal to balanced. And this way is going to give this particular sample less weight, and it's going to give this sample more weight. And then you have ensemble technique. This is very powerful. The idea is this, that you build multiple balanced data set and then build models on them. So suppose you have this data right here, 900 samples of class A and 100 samples of class B. You are going to get random samples from class A and then 100 samples from class B. So you have this data set right here. So feed this data set to a model. Let's call this thing as model 1. Then you do the same thing. You pick up 100 random samples from here. Okay, so this becomes your 100, and then you take 100 samples from here. Okay, so now you have 100 plus 100, this is 200. So now you have this data set right here. You are going to create another model, let's call this thing as model 2, using this data set. So now you have one data set, second data set, do the same thing with the next one, and so forth. So let's say we do up to model 9. So in this particular last model, we took random 100 samples from here, and we took 100 samples from there, and this way you get 100 and 100. So now this will create your model 9. And then at the end, we do majority vote. So when you're making a prediction, you're checking the prediction of model 1, model 2, all the way to model 9, and this way you're trying to guess or trying to infer based on the majority vote. So there is a in your learn library, you can call balanced random forest classifier. That's all you have to do. Just call this library and just give it X train and Y train, and that's going to take care for you all this process. Now I'll show you how you can handle imbalanced dataset using SMORE technique. So first thing you want to do is install your imblearn library. I installed this library and it took me like good, I want to say 1 to 2 minutes before it was installed. After this library is successfully installed, what I'm doing, I'm creating some synthetic data right here. So I'm calling this function called make classification. That's going to generate, that's going to create 5,000 samples for me, and I'm specifying that create only 2 samples, and the weight I want 95% to be class 0, one of the class, and I want 5% to be of the other class. And then I'm specifying my random state. So this way it generates some data for me. This I'm just generating some fake data. After I generate the fake data, I actually want to run. I want to see my first 5 columns. So I just want to see how my my first 5 value they look like. So when I run this, print X first 5 records and also the target first 5 records. So these are my first 5. If you come down over here, these are your first 5. So let's take a look at this one. This is my first row. So in this case, if you count, you will have 1, 2, 3. So there are approximate, well, I think there are 20 of them. So there are 20 features for X right here. For X, there are 20 features. Then you have these classes 0, 0, 0. Okay, I want to know how many class 0 and how many class 1 I have. Well, in this case, I'm using counter function that is from collections library. So I'm supplying the Y, and that's going to tell me how many zeros and ones do I have. So class 0, I have 4,724. They are class 0, and 276, that is class 1. Let's calculate the percentage of class 1. So in this case, I'm taking 276 divided by your total count. That will be 4,724 plus 276. So I'm dividing this thing by this, and the answer comes out to be 0.052. In other words, it's almost like 5% of my data belongs to class 1. All right, good. Let's also plot this thing just to see how it exactly looks like. So I'm calling Seaborn library. I'm supplying my X equal to Y. And when I plot this, you can see that your class 1 is very small. Let me decrease the size of the screen so it's a little bit more visible. There you go. You can see that class 1 is a very small sample. It's not a big sample. On the other hand, class 0 is a big sample. Let me increase the size again. All right. Then I split my data into training and testing. So this actually takes care of that. Now let's step one. Let's train our model the normal way. So in this case, I'm using random forest classifier, and I train the model right here, and then I make some prediction on the X test data set, and then I print out the classification report right here. So when I print out the classification report, if you remember, it's the recall which is the most important. So let's take a look at the recall right now. Recall is 0.55. Well, not a great. Okay, it's doing okay job, but not a great job. So now we are going to be applying SMORT now. So from my Learn library, I'm importing SMORT and create an instance of my SMORT. Then I'm giving it X train and Y train to my SMORT right here. Okay, so it produces, it basically, produces that, using SMORT technique, it produces X train data set, X train and Y train rest data set. Then I'm going to train again. I'm going to train the same model twice now. So in this case, I'm training it with the new samples right here, this one and this one. And I'm asking it to make a prediction, and it makes a prediction. And then I print out the classification report, and look at the recall now. It went to 0.75. So initially my recall was 0.55. Now recall went to 0.75. So observation that this shows improvement in recall for minority class 1. That is good. Now again, just take a look at your accuracy. You do not want to use accuracy in this instance. If you look at your accuracy, 0.95, it's showing 95%, and the accuracy before was 96%. In this case, this is an imbalanced data set. Actually, this is highly imbalanced data set, so you do not want to use accuracy.